right, so let's resolve this issue, and then we'll go ahead and talk about Lab 6. So, in some sense, the source of this problem is that as long as the load line is high, these D inputs can flow through into these latches and come out the Q outputs. And it can race around like this. So imagine something like a D latch, but with one change to it. And this change is going to turn a D latch into a D flip-flop. So we're going to have a D input. And our load line we're going to call a clock. And we're going to draw this funny symbol here. And here's the Q output. And here's what happens with a flip-flop. It's no longer a question of whether this input is 1 or 0. Okay, with a latch, if this is 1, D goes into the device. If this is 0, D does not go in. With a flip-flop, the value of this input does not matter. What matters is when it changes from 0 to 1. So here's what the truth table looks like. And we're putting a new symbol into our truth table, this little arrow, which means when that input changes from a 0 to a 1. And in that case, the output becomes whatever the D input is. So if the clock is low, nothing changes. If the clock is high, nothing changes. But when it makes that transition from low to high, that's when D gets looked at and loaded into the flip-flop. So here's what a timing diagram might look like.
Is that only from low to high, or is it eventually?
Only low to high. So with our latches, remember we were looking at what was happening during this time when the load line was high and Q was matching D. With a flip-flop, it's at this edge when we go from 0 to 1. That's the only thing that matters. So assuming that Q started off low, at this point when the clock rises, D is high, Q goes high. And it stays high until we get here, and at this point D is low, Q goes low. And at this point D is still low, Q stays low. So we've got all kinds of craziness going on with D. We've got short skinny pulses, we've got big wide pulses, but our Q output is very well behaved. It looks at D here, it looks at D here, it looks at D here. And it ignores it every other time. So that's what a flip-flop does for us. And so imagine this circuit built with flip-flops, bless you, instead of latches. If these were all D flip-flops, go back to the original setup. We had a 5 stored in here. The 5 came around, 1 got added. We had 6 coming into the D inputs, totally ignored until this clock input raises to a 1. And at this exact point, that 6 gets loaded into here and it comes out of the Qs. Now it immediately races around, goes in the adder, 1 gets added to it, and we have a 7 sitting here at the D inputs, but that doesn't change anything. Because this event has already occurred, and as long as this stays high, nothing changes in these flip-flops. And when this goes low, nothing changes in the flip-flops until eventually the clock goes high again, and now that 7 gets loaded in. Now we've done another x equals x plus 1, The 7 races around, gets 1 added to it, becomes an 8. 8 goes to the input of the Ds, but doesn't affect anything. And the output can drop low, and when it raises high again, then the output will change to 8. We've done another x equals x plus 1.
Wouldn't that still be a small window that could cause error when we're working out that clock?
How so?
Could leave it on just for slightly too long and get an extra 1 in there?
See, if we leave this on for 5 years, nothing's going to change.
But it's every time the clock went up.
When it goes up, but if it goes up and we leave it up, then these flip-flops don't change their outputs,
Gotcha.
right? So we can leave it up as long as we want, and nothing's going to change. It's only during that transition, and we can leave it down as long as we want, right? So one way to think about this is these latches, these are what we call level triggered. The action happens based on the level of the load line, whether it's high or low. Flip-flops, these are edge triggered. The action happens on this rising edge, and only there.
I'm confused in just knowing, from my understanding of the clock in the previous lab, is that it just continuously goes up and down.
Mm-hmm.
So it doesn't make sense that a clock would stay up or not go back up again.
Well, so we wouldn't leave it up for 5 years, but if our circuits can respond in 10 picoseconds, and this is high for a microsecond, that's effectively 5 years.
All right.
Right? It's on long enough that there could be lots of these kinds of things happening. But sometimes we have a processor and the clock actually stops. Like if it's going into a power saving mode, right, it'll actually suspend the clock for a while. That's one way to cut down the power drain. All right, so these are edge triggered devices, and this thing that we've been talking about, we could actually call positive edge triggered. Positive edge triggered means when the input raises from 0 to 1. You can also get negative edge triggered devices, and they do what you would guess. They have the action when the clock changes from 1 to 0. So they would trigger on this edge. And when you draw a clock, you usually draw this little triangle to indicate that it's edge triggered. And if you want a negative edge triggered clock, we just draw a little bubble next to the input. Because really all you got to do is just feed the clock through an inverter, and your positive edge now becomes a negative edge, and vice versa. Yeah?
So are these a part of computer circuitry?
Yes. So this is getting into what we would actually see inside the data path of a computer, for example. And this is not a bad drawing, actually. It's only 4 bits instead of 64 bits, right? And it's only a circuit that's hardwired to add 1 to some number. But we know about multiplexers, right? We could have several of these registers, X, Y, Z, and we could use multiplexers to choose which of these Qs go into the input of this adder. And by setting those multiplexer select lines, we could make this same circuit do X plus 1 or Y plus 1 or Z plus 1. Yeah.
So you can have like feedback loops with like multiplexers.
Oh yeah.
Just routing things.
Yeah, absolutely. And that's exactly what we're going to see. And let me see if I can find really quickly. And I'm gonna go through this in more detail another time. Here we go. So this is the heart and soul of a very famous computer called the VAX 11780. This was what drew me into computers in a unique way. And it's all feedback paths and multiplexers, right? So these are multiplexers. They have different inputs coming in. This is an arithmetic logic unit. So you can select what you want to do to these two inputs. You can shift the output. You can send the output here and do some more muxing and send it into a mux here and put it into here and send it into a mux and bring it back in here, right? So lots of feedback. And this is basically how the CPU did all its things. If you had an instruction that said increment this register or compare these two registers, and if they're equal, go to some other place in your code. All you had to do was set up all of these select lines on these different multiplexers. And so this was called the data path, and it basically is just a big steering network. And it's similar in spirit to this goofy drawing that we've done here, right? Basically the same idea, just a lot more control over it. And this was how I spent my life when I was an undergrad, because we had permission to take this machine apart Saturday nights, so we would do all sorts of horrible things to it. And we had to bribe a field service rep to get that documentation because it wasn't available at the time. But
Okay, cool. Now we know how to
Yeah.
continue our education.
oh yes, totally, yeah,
Bribing people.
yeah. Well, we had a CCD device, right? A really old image processing system, but this was in the 70s, right? There was no digital cameras or anything, but we figured out how to hook this thing up and use a microprocessor and basically load in an image, and then we could convert that and get a copy on a hard printer. So we had a crude digital camera, and so we took a picture for this guy and gave him a printout of it, and he thought that was really cool, and we're like, any chance we could borrow that little book you got there? And he's like, sure. So it was good. It was a good cause. All right, so yeah, so this is basically what's going to be going on inside our computer systems. So edge-triggered devices are going to be the key to all of this, okay, because they eliminate this potential race condition. And we've introduced this new terminology here, a clock, right? So this is synchronous logic, right? Wasn't a big surprise. Asynchronous, no clock. Synchronous, we have a clock. When you go to Best Buy and you look at laptops and it says, 2.3 gigahertz, that's what it's talking about. Okay, the main clock that's driving the CPU has a certain frequency it runs at. And that clock rate basically says how often are things allowed to change. How often, when we have this feedback path and we have the output of an ALU coming back into the input, how often do we let that trickle through and become the next set of changes? And if you have a 2.3 gigahertz clock, generally the clock is 2.3 billion ticks per second.
How come sometimes newer CPUs come out and they're slower clocks, even though they're supposedly better?
Yeah, that's a whole nother discussion. That's a whole course, actually, called computer architecture, right? So clock rate is partially a marketing term, right? If you have a really big number next to your clock rate, people will pay more money for it. But it doesn't necessarily mean that things are faster, right? So that VAX that I showed you had a clock rate of 1 megahertz, right? 1 meg, that's 1,000th of a gig. That's like 1/3000th of what my little laptop here does. But it was a really powerful machine because what it could do in one clock tick was this. And what a modern CPU, like in your cell phone, can do in one clock tick is like this, right? So clock speed is only part of the story. Plus there's all kinds of other factors. If you have enough power available and you have a liquid nitrogen system to cool your cell phone, you could run it really, really fast, right? But it's going to be room size because of the cooling system, and it's going to cost you $1,000 a month in power bills, right? So extreme example, but there's all these different variables that come into it basically. And sometimes for clock rates on laptops, it's just price, right? You get something with an Atom processor and it runs at 900 megahertz because that's all the CPU hardware will actually support. But it's cheap, it doesn't take a lot of battery, it gives you a long life for your netbook or whatever.
I was just gonna say, that's why people up the voltage on their CPUs and overclock them and then add water cooling.
Yes, yes, totally. Okay, we are recording good. So yeah, so we'll talk a lot about clock rates on Thursday, and actually throughout the rest of this course. But you're really talking about how quickly these devices like flip-flops can respond, and how quickly these kinds of things can happen. And if you have multiplexers in here, or you have something more complex than a 4-bit adder, right, everything has propagation delay. And we wouldn't want to clock this so quickly that our output from here hasn't had time to get 1 added to it and come back in. If we tried to clock this in 1 nanosecond, it's probably not going to work if we're building these things with chips from our parts box, because we know that all these things take, 5 or 10 nanoseconds to generate correct outputs. So there's a maximum clock speed involved, and it's related to the hardware. And it's related to other things, right? It may have a good average performance, but there may be a really horrible worst case time, where if you've got a bunch of 1s and you're adding 1 to it, it takes a while for those carries to ripple all the way down, and you need to set your clock based on that worst case. So when you're overclocking, you're playing a gambling game, right? You're saying, well, hopefully that worst case doesn't apply, or if it does, it's not something super critical. So you turn up your clock a little more, and at some point your game starts to glitch out a little. And maybe it's a big glitch, maybe it's a little glitch. But at the same time, you're also starting to heat your circuit up, so you're trying to cool it. And usually what will kill you when you overclock is you'll smoke your CPU, right? You'll physically damage it. All right. So we've done this, and we've talked about race conditions. We've started to talk about flip-flops. Let's talk about Lab 6. And then if there's time left, we'll start talking about specific types of flip-flops, and we'll go on from there and continue on Thursday. But let's get through the next lab. Yes?
Did you say you put homework up before class?
Yes, so there's homework posted on Canvas.
Do it be Thursday?
I'm making it due Tuesday, but I put some notes in there saying please try to do the ones that you can do before Thursday so that we can talk about them. And the ones on state machines we probably can't do, and I don't know how far we're going to get on flip-flops today, but at least look at them so that you have things to keep in mind as we're going through material. We definitely won't get to questions 6 through 11, but look at the first few questions at least and think about them. And if we haven't talked about it, don't stress over it, right? But put it in your brain. You can read ahead in the book too, right? So this is all chapter 4 in the text. So. All right, so lab 6, we're back to the traffic light. We're going to finish it up. So there's 2 experiments in here. The first experiment is to build a delay circuit. And let me tell you what this delay circuit should do, and then we'll talk about the details. But here's a system diagram. Very simple system diagram. Something goes in, something comes out. Let me show you a timing diagram. So your input basically describes what your output should be, but there's a bit of a delay. And it's not just a propagation delay, it's 2 to 4 seconds of delay. So your input goes high, and let's say 2 seconds later, your output goes high. And your input goes low, and 2 seconds later, your output goes low. And so this delay here, 2 to 4 seconds. So a noticeable delay. So how do you test your delay circuit? Put a switch over here, or just a wire that you connect to either high or low. Put an LED on the output. Okay, connect your input to ground, your LED should go off. Connect your input to power, stand back, wait for 2 to 3 seconds, your LED should turn on. Switch your wire to ground, stand back, 2 to 3 seconds later, your LED goes off. Okay, that's experiment 1. So it's a delayed input to output buffer. So how do you do this? Well, you're going to use the 74 LS374. This is a set of flip-flops. So it's a set of what we call D flip-flops. And we'll talk about D flip-flops shortly. But basically, so 374, yes. So this picture down here. So we're going to have a clock going in. And here's the deal, these D flip, well, we already know about D flip-flops. So look at this block up here, block H. There's a D input, there's a Q output. Okay, and the clock is being driven from pin 11. So when pin 11 changes from 0 to 1, whatever's on pin 18 will appear on pin 19. Okay, and it only looks at it on that rising edge. And then D can change, doesn't make any difference until the clock drops, and then it goes high again, and then whatever's on pin 18 appears on pin 19. And you've got 8 of these flip-flops in here. Okay, so pin 13 goes up to 12, pin 14 goes to 15, D's your input, Q's your output. And there's details in here on how exactly this works. So your output control has got to be low. So that's pin 1, I believe. That's got to be low, otherwise if it's high, your output isn't asserted. It's in state Z, which means it's not a 0 or a 1. So pull your output control to ground, just hardwire that. And then every time the clock rises, if D is high, the output's high. If D is low, the output is low. Okay, so this is one chip. It has 8 of these flip-flops that we've been talking about. And how do you get a delay circuit out of flip-flops? You connect them together.
Oh, we can't see.
Just gonna make you read my mind. So suppose we build this circuit, 2D flip-flops. Our input to our delay circuit goes into the first flip-flop's D input. The Q output goes into the second flip-flop's D input. And the Q output from there, that's our output from our delay circuit. So just think through the behavior of this. Suppose our input is 0. This clock is pulsing, let's say every 2 seconds. That 0 is eventually going to get loaded into this flip-flop. We get a 0 coming out. That 0 goes into the D input here, gets loaded in, we've got a 0 coming out. So if you set your input to 0 and you wait a few seconds, your output's going to be 0. And let me call this point in the middle, I don't know, we'll just call it B for in between. is our clock. All right, let's suppose that over here I raise my input to a 1. So nothing happens until we get to this rising edge of the clock. So up to this point, B is still low and out is still low. At this edge right here, stuff happens. So what changes in our system on that rising edge? Just B. This first flip-flop, the input is 1, it has been 1, so we have a 1 on the D input, and when the clock rises, we're told Q is going to change in response, so B is going to go high. But here's the really, really, really cool part. At the moment when the clock ticked, B was 0. Which means that the output of this flip-flop is still going to be 0. So this is going to stay low. Now right after the clock ticks, B changes to a 1. But that's after this event has happened, right? This is a knife edge. Tick. And at the moment of that tick, we look at what everything is input-wise, and then we figure out what the outputs are. And at that moment, this D input is a 1, this D input is a 0. So this becomes a 1, this remains a 0. Now we go on to the next clock tick. And B is going to stay high, right, because the input is still a 1. But at this clock tick, since the B input is 1, the Q output's going to change to match it. The output's going to go high. And that's the delayed response we're looking for. Our input raised here, our output raised here. And now if our input drops low, then at this edge, B will drop low in response. But at this edge, B is still 1, so the output will stay high. And it's only when we get over here to this next rising edge. At this point, B is a 0, so the output will drop low. And so again, we've got this delayed response. Our input dropped here. Our output dropped there. So that's your delay circuit. And if you think about it slightly deeper, the reason, if this clock is rising every 2 seconds, right, which is what your 555 did in the last lab, the reason this delay could be anywhere from 2 to 4 seconds is because if I change my input right after this rising edge, it's going to take almost 2 whole clock ticks before my output changes. If I change it right before this rising edge, it's going to take just slightly over 1 clock tick before the output changes. So because I don't know where I am between the 2 clock ticks, right, it could be anywhere from 2 to 4 seconds, which is exactly what we want. So this gets you experiment 1 basically, but it's a really cool circuit once you've got it built and you play around with the input, put an LED on the output, right? It's a true time-aware circuit. It's the first circuit we're doing in here that doesn't just basically respond as quickly as the circuitry can catch up with the inputs. Okay, we're actually putting in a deliberate delay. So that's experiment 1. Okay. So assume the 555 is configured to generate a 2-second pulse, which you've hopefully still got from your last lab. If not, you get to rebuild it. And then use that to implement the 2 to 4 second delay. You can never implement a 555 too many times. Yeah.
Is this on the same due date, Tuesday, like usual?
Check Canvas,
Okay.
because one of them is changing soon, but I think this one is Tuesday.
Okay.
Actually, I have Canvas up, so let's see. Looks like May 22nd, so that's,
Next
Yeah,
week.
next week.
yeah. And then big long gap before Lab 7. And then a week to Lab 8. Lab 8's the optional one. Yeah, it's coming fast. All right, so you got experiment 1, 2 to 4 second delay circuit. All right, we're going to use that to do experiment 2, which is basically your traffic light with a yellow light with, guess what, 2 to 4 second delay on the yellow light. Not a coincidence. Okay, so this is one of these things where if you go into the collaboratorium and you listen to what other people are saying, you're going to hear all kinds of things. And a lot of it's going to be really horrifying, okay? And you can ignore it, okay? There's a very straightforward way to do experiment 2. Straightforward doesn't mean easy, okay? It's straightforward to knock down a brick wall with your head. You just keep hitting it until the wall comes down. It's not easy, but it's straightforward. We can describe a straightforward way to do experiment 2. It's at least a 2 protoboard experiment, okay? So it's going to be lots of chips and lots of wiring. But the design and the theory of how this works, we're going to get through in about 10 minutes here, okay? And there's lots of other ways to do this besides what we're going to talk about in the next 10 minutes. And there's a note in here which says there are multiple design options, okay? Many of them horrifying. We're going to talk about a fairly straightforward one. And the fairly straightforward one is to use your previous 3-way intersection circuit and add something to it to create the yellow light behavior. And it involves using a timing diagram with your delay circuit, but we're gonna draw our own version of this. And if you decide to go this route, you want to explain this procedure in your lab report. Don't just put in this big horrible circuit with 80 billion chips and a sign-off sheet saying my circuit worked, okay? Tell the reader what the design is, why you're doing this, okay? So you're gonna want pictures, timing diagrams, whatever it is that helps explain this. The reason for doing that is because in writing that, you're forcing yourself to understand it as well as possible, okay? So great way to learn the stuff is by trying to explain it. So explain it to your imaginary reader and you'll understand it better. All right, so here's the setup. Over here is your old, thank you, your old traffic light circuit. And it's got sensors. And it's got outputs. And I'm cheating, I'm only showing 3 outputs, just the green lights for west, south, and east. And in your old circuit, right, this is equal to 1 if that direction has permission to go. So if green south is 1, that meant that you were going to give permission to the car on the south to go through the intersection. Okay? We're going to pick off one of these signals and we're going to add a yellow light to it. But you're going to do this for all 3 of your signals. Okay, we're just going to think about one light at a time. And if we know how to do this for, say, green east, you do the exact same thing for green south and green west. Okay? But this is your old traffic light circuit, so you need that circuit, and you need the signals that came out of there that used to drive your green lights. Okay, so that's a relatively small circuit if you reduced your equations. So let's just think about green east. We'll just think about one lane. Okay? So I'm going to call this go. And I'm going to put it into a delay circuit. And I'm going to call this DGO, delayed go. And we want to look at how the values of go and delayed go compare to each other and what that means. So this is what this diagram is alluding to in here. But I prefer to think of it as we're going to do it here. So let's make a truth table. And there's only 4 possibilities for the combination of go and delayed go. And my output column I'm going to call meaning, and we're going to put words in here maybe, and describe what's happening in each of these 4 possibilities. So possibility 1, your go signal is 0, which means the green light from your old circuit was off. Okay, which meant that right now that car does not have permission to go. Suppose the delayed version of that go signal is also 0. Can we conclude anything from that?
Red light?
It's a red light, right? What this is telling us is that 2 to 4 seconds ago, this lane did not have permission to go, and right now it does not have permission to go. So it's not allowed to go now, and it wasn't allowed to go a few seconds ago. This is a red light. Does everybody see that? Let's go down to our 3rd row. The delayed go signal is still a 0, but the go signal is now a 1. So we're being told by the old lab circuit that, hey, this car should have permission to go, but we know that 2 seconds ago it did not have permission. So what's happening right now?
Green light.
It could be green, but we just got permission to go 2 seconds ago. Do you want to turn green that quickly?
Means it's yellow.
Yeah, it's red.
It's red. It's like a yellow, right? But we don't have a yellow from red to green, right? So this is still red, but it's heading to green soon. Now, after a few more seconds have passed, the go signal is 1 and the delayed version of go is also 1. So we know it's been 2 to 4 seconds since we had permission to go. So what do we do here? We go. All right, and then 2nd row, the go signal is 0. We're told we don't have permission to go, but we know that just a couple of seconds ago we did have permission. That's a yellow light. That's all you need, right? Take the output from your old traffic circuit and compare that output to a delayed version of that output. If they're both 0, make your light red. If they're 0, 1, make it yellow. If they're 1, 0, make it red. If they're 1, 1, make it green. Does that make sense? And this is a much easier approach to this than the approach that we'll be working towards in the next few weeks, which is to use a state machine. Because the state machine approach becomes this. Occasionally somebody actually does this, usually because they missed the lecture and they didn't do the lab in time, and they panicked the night before, and so they just jumped into it, and they get, 6 proto boards, and sometimes it works too. It's great. But we're using an observation about this signal and how it changes over time to tap into this delayed light behavior. So yes.
With this one, are we still gonna be using like a switch to make sure it's green on that one?
So since this is coming from your old circuit, right?
Yeah.
You know that only one of these is going to be 1, right? And so you're going to have 3 of these things and 3 of these things, 1 for each lane.
Gotcha.
And your old circuit should take care of making sure that only one of these is going to get green. So now we're back to something we've done a few times, but let's redraw this truth table. So 0, 0, we said we want that to be a red light. So red should turn on, yellow and green should turn off. 0, 1 should be yellow, so yellow turns on, red and green turn off. 1, 0 should be red, so red's on, yellow, green is off, and 1, 1 is green on, red and yellow off. And now we can forget about traffic lights for an hour and just say, hey, here's a truth table, 2 inputs, 3 outputs. Let's build a circuit that generates these outputs. Connect this to a red LED, yellow, green. Feed go from your old circuit. Run go through your delay circuit from experiment 1, take the output, use that for this input, and you're done, right, with 1 lane. And then repeat this for the south permission signal and the west permission signal. So you got 3 delay circuits, 3 of whatever circuit you have to implement this, and 9 LEDs. And then it's fun when it works. So you have 3 switches for your car sensors, and you flip a switch and you should see the lights change in a reasonable way. Does that make sense? And so this is one of these things where if you look at the final circuit diagram, it's not going to jump out to you, oh, this is a traffic light controller. Oh, this controls a yellow light, right? We're thinking in higher level blocks. We're thinking in functional behaviors. We're thinking of this delay unit and what it does, right? We're not looking at the D flip-flops inside here when we're trying to figure this out. We're thinking of the behavior of this block. It takes us in, it delays it, it generates a copy of it later in time. We're not thinking of the circuitry inside here, we're just thinking this is something that tells me if East has permission to go, right? And when we build circuitry for this, right, same thing, it's just something which realizes this truth table. So you gotta have a lot of faith when you're doing this and you're putting your circuit together that it's going to work. But you can build it in pieces. So you build your delay circuit first, that's experiment 1, it's actually a separate experiment. And then you can build your delay circuit plus this logic and forget about the traffic light controller, right? And you should see this kind of behavior. If you give the car permission by putting a 1 in here, it should wait a few seconds and turn green. When you take away permission, it should turn yellow for a few seconds and then turn red. And once that's working, then you just make 2 more of these and you hook them up to your old traffic light controller for the green lights, and you're good to go. So questions?
So when we build a truth table, can we do you want us to break it down to each light, or can we just have one since they're essentially the same thing?
One what?
Or the truth table, one, say that, or do
Like
does
this?
does
Well,
each
ultimately, you
circuit
need to build circuitry, which means you need to write equations for each of these LEDs.
right.
So you need to bring it into this level at some point. But certainly while you're developing it in the lab, right, this is a good intermediate level to have, and you want this handy so that when you're trying to debug it, you can go back and look at this and know what's supposed to be happening. Yeah. And you know, while you're building it, throw an LED here, throw an LED here, and you got 2 to 4 seconds to see what state the system's in and see if it's right or not. If you really want, you can change the speed of your 555 and make it 5 to 10 seconds delay, right? So it's easier to work with. And remember, your delay circuit needs a clock going in, so this is going to come from your 555 pin 3. Yeah.
Split our 555 to all of them, or do we need multiple?
You can use one 555 and use that same train of pulses for all 3 circuits.
Sounds good.
Yeah, because that's agnostic to what's going on. It's really just generating pulses. All right, that's lab 6, and then you're done with traffic light for a few weeks. Then it comes back. It comes back in the optional lab. So the optional lab 8, we're gonna get through this on Thursday, and Tuesday talk some more state machine analysis maybe, and then talk about state machine synthesis. And then we're gonna move on to talking about something called Verilog and hardware definition languages and FPGAs, which are programmable devices where we can take all of this traffic light stuff and put it inside one chip. And your optional lab 8 is going to be to redo the traffic light experiment with an FPGA. And if you do that, the wiring becomes really, really straightforward. If you do that, your circuit's going to end up looking like this. And it's just this FPGA and a bunch of wires. And you get to use the test bed. So I've got a test bed in my office I'll put in the collaboratorium. But it's got 3 cars, and it's got magnetic sensors, and it's got a traffic light. And you can drive a car up to the intersection, and it'll trip the sensor, and you can hook that up to your circuit, and it'll change the lights.
They'll
It's
crash.
fun to play with. Yeah, or you can crash them all. So we'll play with that probably the last week.
Is Lab 8 always optional, or is it just
Lab 8 only. This is the first year Lab 8 has existed.
Oh, cool.
So you are guinea pigs.
Extra credit is always
Extra credit guinea pigs though.
Yeah.
Good deal.
No worries.
All right. Have a good one. I will see you on Thursday.